presentation, we're going to look at fossils and their importance. And really, the whole importance here is that they help scientists know what life used to be like. Of course, nobody was around in prehistoric times to give an accurate account of what was happening on the earth or in the earth, be it on the surface or living things. So scientists use many different clues to help them figure out what was going on way back in prehistoric times. Most people think of fossils as just being bones, specifically dinosaur bones. But really, anything that's a remain or evidence of something that used to be living can be a fossil. Most of the time, we find these fossils in sedimentary rocks, and those are the rocks that are made through compaction and cementation of sediments. Here are some other examples of fossils. Fossils, of course, can be found in rock, like the picture on the top left. They can also be found in amber, such as the picture in the top middle. Amber is basically hardened tree sap, and so as the sap runs down the tree, it may run over and harden any insect that's on that tree. In this picture, it looks like maybe a scorpion has been caught in the amber. Petrifaction is a process that takes the soft part of the soft part of an organism and replaces it with mineral and basically turns it into a rock. The picture on the top right is actually a piece of wood, and if you would feel it, it would feel like a rock. It's very solid. Fossils can also be found in asphalt, such as the picture in the bottom left, or frozen in ice, like the picture in the bottom right. There are other things that can also be fossils. Animals that leave behind their footprints, such as the picture on the left, this would be considered a fossil. Also, animals burrow, meaning that they dig underground. So the openings that have been left can be a fossil. And as gross as it may sound, the waste of an animal can also be a fossil. Now, you may be asking yourself, who cares about a bunch of fossils? They're old and they're dead. But believe it or not, fossils are very important, specifically for the three reasons you see before you. They help us know what life was like many years ago on Earth, because of course no one was around to give a first-hand account. They help give us clues about what the environment was like, and they show us how much has actually changed over time. Clue number 2 that scientists use to help them study the past is the geologic time scale. This basically takes the whole history of the Earth and divides it into smaller, more manageable pieces of time. So you see some examples of those listed on your screen: an eon, an era, a period, an epoch. Those are just all ways that we divide up Earth's history. Here's an example of a geologic time scale. The way that you read this one is from left to right. So on the left-hand side, the real skinny white column you see is broken into 4 different eras. And so these are the bigger chunks of time. Those eras then, as you move to the right, are broken down into periods. These are smaller pieces of time. So it's just an easier way to talk about a large section of time. It's very similar to the way that we divide our year up. A year is a big chunk of time. That's 365 days. And so to make it easier to talk about those days, we use a calendar. And so we break a year down into months. Months can be broken down into weeks, and then weeks into days, and we can even go down further into 24 hours and so forth. It just makes it easier to talk about when you're talking about such a large chunk of time. Scientists also use something called relative dating. And this helps them give an approximate age of a fossil or an event that happened in history. Because, of course, nobody was there to know for sure, so scientists have to make their best guess. And so what relative age is they try to figure out the age of the fossil compared to something else. They don't know an exact number, but, for example, they may know that one fossil is older than another. So that would be its relative age. Now here's a silly question. Which one of these people do you think is older? Of course, it's the man on the left. We don't need to know exactly how old it is to know that he is obviously older than that little girl, and that would be his relative age. And that's what's useful to scientists. They don't exactly know how old one fossil is, but they can compare it to another and see if it's older or younger than that fossil. Scientists also use something called superposition. Sounds like a superhero, but not quite. Superposition means that when you've got layers of rocks, one on top of the other, any rocks that are lower in those layers would be considered older. Therefore, if they find fossils in those rocks or in those layers, they would be older than anything above it. So this picture shows us superposition. So if you look at the top, you see somebody walking on the surface. So that's showing you that that is the top where you can see layer 12. And then going down, the layers get older and older. So towards the bottom of this, all those layers, 1, 2, 3, and so forth, were all put down first. And as you go up, they get younger. So if I'm looking at row 2 and I see that seashell fossil, I may not know exactly how old that seashell fossil is, but I know that it has got to be older than the footprints that are up in layer 9. And the reason I know that is because it's lower. It's closer to the bottom, which means it was put down first. That's the law of superposition. That last picture we saw, all those layers were in nice, neat layers. But unfortunately, that's not real life all the time, because there's a force at work, and we've learned about that force, which is erosion. So what happens is erosion comes along and moves a lot of those sediments which are in those rows. And so when those rows go missing, or there's gaps or missing parts to them, those are called unconformities. So this diagram will show us how unconformities work. We're going to start at the picture at the top. You'll notice that there's nice, neat layers there, and those layers represent layers of rock and sediment. The second picture shows us that forces inside the earth are pushing up, probably some kind of convergent boundary there, maybe going up to form a mountain. The third picture down, we see though that now some of those layers are gone. So probably erosion has come and over time worn down that mountain into a plain or plateau, it looks like. And then once those pieces are away, the bottom picture shows us that new sediments have been added. That's what those gray layers are. And so this shows us how unconformities happen because of erosion. Lastly, scientists use something called index fossils. Now, index fossils are very useful because they are a fossil that were only around for a short period of time. Now, what's a little deceiving, though, is when a scientist says short, that could mean 100,000 years. But when you're talking about the history of the Earth, scientists think it's like 4 billion years old. So 100,000 years isn't that much. But these index fossils are important because when a scientist finds them, that it really helps them narrow down what time period that organism lived. One example of an index fossil is the trilobite that you see pictured here. Remember this guy? Psy, Gangnam Style? So we're going to use him as an example for an index fossil. Let's say you were to find a photograph and he's in it. Well, you may not know how old the photograph is, but what you do know is that Psy was only popular for a short period of time, maybe only a year or two. And so it really helps you narrow down to know when that photograph was taken. He wasn't popular 50 years ago. He hasn't been popular very recently, but just within the last year or two would we guess that the picture was taken. And so that's what scientists use to help them when they're studying fossils to know how old fossils are. If they know it's an index fossil, then that helps them narrow down when it lived.